All right, so let's begin chapter 6 of the Woolder's textbook, Multiple Regression Model Further Issues. So in this chapter, we're going to talk about different topics, including different functional forms for the model, finally talking about adjusted R-square, and talking about interaction terms, and lots of very interesting and practical things in this chapter. So what I recommend you to do is that, while you're watching the videos, have the RStudio open in front of you and pause the video, try to apply whatever you learned from the lecture videos in R, and then try to practice what you learned. So this is really important because this is one of the most exciting and more practical chapters in the entire textbook. So I want you to pay very good attention. Okay, but before that, before we start the discussion, I want to walk you through to this, let's call it our cheat sheet for different functional forms, and quickly walk you through what is the motivation for us to use different functional forms. So we have seen at least 3 of them before, so the 4th one is going to be a new one, but let's see what do we have. Let's name them. Number 1. This is our linear model. Well, all of them are linear, right? Because if I want to say that the model is linear, I'll look at the betas, right? If the model is linear in beta, then it's assumption number 1. We have linearity in parameters. So we have log models, we have quadratic models, and we have models with interaction terms. So this is what we call interaction term when x1 multiply x2. So this is going to be a very quick cheat sheet for you guys, and I don't expect you to understand all of it right now because we haven't started the discussion yet. But while you're going over the slides, I want you to come back to this page and see if you can connect the dots. Okay, but let me quickly walk you through to the motivation. So imagine it all comes from a data, right? As a researcher, you have let's go back to our wage equation. Let's say we have wage versus education. All right, so it's a function of education, maybe gender, I don't know, maybe experience, and etc. Right? As a researcher, you want to start from some point, right? So the very basic model that you can start with, you're going to say that, okay, you know what? Let's say wage is equal to beta 0 plus beta 1. Education plus beta 2, gender, well, let's call it female. It's a better name because it's going to be a dummy variable. If it is 1, it's female. If it is 0, it's male, right? Plus beta 3, experience, and etc., right? This is going to be the most basic model. Actually, this is our first model. The model is linear in parameter and also linear in explanatory variables. So when do we use this model? Whenever you have no idea about the functional form of the model, you want to make any assumption. You say that, okay, everything is linear, and let's put it that way, right? So you believe that, if you want to plot wage versus education, for example, it's something like this. You believe that the relationship is something linear. So if you believe that it's like this, we use our first model, linear explanatory variables as well, right? So this is the one that I'm talking about, this one. However, if you think that, so let's talk about the second one. If you think that the relationship between wage and education is not that simple, if this is wage, if this is my education. If you think that the relationship is something like this, for higher level of education, the wage is going to increase, but at an increasing rate, right? So it seems that there's this relationship between education and wage, right? So if you look at the slope is changing, right? The slope is increasing. So for these models, if you believe as a researcher that the relationship is non-linear, so we had 2 ways, right? So we said either you can use the log version or you can use the quadratic version, right? Quadratic. So what was the log version? We say, okay, instead of wage, use log wage. So if I use log wage, then it's transformation of the data. Maybe the new data looks like this, and then I'm going to use my fitted line, and everything looks fine. That was one way. So basically, this is model number 2. If you use log transformation, and then we said that, okay, you can, instead of log, you can stick to the wage and education, and instead of, let's say, changing the, manipulating the data, let's bend the curve itself. How do I do that? By using a quadratic version. So if I say, for example, wage is equal to beta 0 plus beta 1 education plus beta 2 education score, right? Why did we do that? Because we believe that, wage is increasing with education, but an increasing rate. So so for higher level of education, the wage is going to be higher. So that was the motivation. Okay. So we have seen all these things before, right? So there's nothing new here. So this is our model number 3. But what is the motivation for model number 4 when we introduce the interaction terms? So imagine you think that this is the wage, this is education. Imagine the blue dots that I'm using is the wage for male in the data, and the red dots that I'm showing is the wage for females in the data. Imagine that's the case, right? Again, you come to the question with some prior belief, and then you will decide which model you should pick. If this is something that you believe, then you say that, okay, there must be a line for males and another fitted line for females. In another term, what are you saying? You say that, okay, let's fix the education. Imagine you're talking about the bachelor students, right? And it seems that the bachelor males are receiving higher income than bachelor female. Again, this is if you believe that there is any kind of wage discrimination in the data, then you have to use another functional form. So you have to say that, the effect of education on wage does not depend on education anymore, like this one. Or it's not constant anymore, like this one. Here, the effect of education on wage is constant, right? The effect of education on wage is a function of gender as well. So it has something to do with the interaction between education and female. So when that's the case, you want to go ahead and say, okay, let's rewrite the model like this. Wage is equal to, let's say, beta 0. I have education in the model. I have gender in the model. We call it female. And also, here's a new term. I need to put the interaction between education, multiply, and female in the model as well. Because if you want to get something like this, you have to use the interaction term. So this is very, very interesting. And I think this is something new for most of you guys, right? So we will add interaction terms to the model if you believe that the partial effect of education on wage depends on some other explanatory variable, in this case, female. Okay, so that's the motivation for model number 4. So let's quickly go back to this cheat sheet and review what we said by looking at the partial effect of x1 on y. So if you believe that the partial effect of x1, let's say education, on y, let's say wage, is constant, is fixed, we use model number 1. If you believe that the partial effect of x1 on on wage, on y, is a function of x1 itself, let's say effect of education on wage is a function of education, we use model number 3. If you believe that the partial effect of x1 on y is a function of some other explanatory variable, x2 like gender, we use the interaction term. And if you want to have some, let's say, interpretation in terms of percentage, we use the log model, right? So we will talk about different properties of log. It's not only the interpretation, it has very, very nice properties. It helps us to shrink the distribution. It helps us to get rid of heteroscedasticity. It helps us to get more normal residuals. So these are the things that we have covered in the previous chapters as well. So that's why we are really interested in these log models as well. Okay, so this is a big picture of this chapter. Again, throughout the lectures, I will walk you through multiple examples for each of these different functional forms, but I hope that in terms of motivation, it is clear for you why we needed to do something like this, right? So it depends on what is your prior belief. What do you think the relationship between your explanatory variable and your dependent variable is, and you start from there. Sometimes you have no idea, and to be honest, most of the time we have no idea because the data is not two-dimensional or it's not three-dimensional. The data is 20 dimensions, 100 dimensions. We have no idea what's the exact relationship between variables, right? If that's the case, like your final project, you're gonna try all of them. You're gonna try all of them and see which one has the highest adjusted R-square. So we're gonna look at the R-square. We put a bar on top of it. We call it adjusted R-square. So from this lecture onward, instead of R-square, we will be looking at adjusted R-square because that's a more reliable statistic to look into if you want to compare models. Okay, and let's see quickly how we can do it in R, and then we will start our discussion in the next video. So application in R, super easy. So the first one, we use the LM function, LMY tilde x1 plus x2, and then you pass the data frame, right? For log models, if there's log y here, log x here, log x1 here, you just simply add the log, open close parent, and then done. For the quadratic models, if we use this, make sure you use this I function, and then x1 to the power of 2. The rest of it is the same. And so maybe the only new thing that you haven't seen before is this. How can I put the interaction terms in R? So if you want to write this equation in R, you will say, okay, regress y on x1 and x2 and x1 column x2. Okay, so this is how we do it in R. So basically, for example, if you want to write this in R, so you have to say education column female, the name of the exponential variables. Okay, that's it. So I hope that you are as excited as me because this chapter is super practical and useful, and we're gonna have a lot of fun. See you in the next one.